I would like to start by thanking the organizers for inviting me to give a talk for here. So this talk is based on works of two students who just graduated last year, Maity and Avishek Ghosh. After graduating, Avishek graduated from UC Berkeley with Kannan Ramchandran, and he joined UCSD as a postdoc. Did I lose my slides?
Yeah, they just disappeared.
Okay, I'm sorry about that. I think.
Oh, now they're back.
Yes, and Raj was my student in UMass Amherst who graduated last year, and he joined Microsoft. So we are going to talk about distributed optimization in a very specific setting, but it is sort of universally used where there is a central server, and this is data-driven optimization for the purpose of machine learning training. So this is the usual setup where you have a central server that keeps track of a model or a machine learning model. And the data is distributed across many users or many worker nodes or many different machines. Now, sometime to train a large scale model, it is necessary to parallelize this thing. So we distribute our task among several GPUs or whatnot. But there are like other upcoming paradigms like federated learning, where data is inherently distributed. They are not supposed to be in one place anyway. So in this type, this has been a pretty standard and popular distributed optimization topology for the past few years. So each user or each machine, they compute something on local data. They send the result to the central server. The central server aggregates the result, updates the model, and then sends the model back to or broadcast the model back to the users. They again compute some quantity based on their local data, sends back the result, and this iterative process usually continues. Right. So the method of choice in this type of optimization problem happens to be stochastic gradient descent, which is a simple first order method, a stochastic first order method, where each local machine actually computes a stochastic gradient and estimate a random variable, a random vector, which in the case of, like in some cases, it might be an unbiased estimator of a subgradient of the actual function. And it turns out if that is the case, then for convex function, this iterative process converges. And it's like there are many results of this flavor that can be used. I just picked up one from this paper by Shamir and Zhang, where under this type of convexity and bounded gradient conditions, you can have convergence, and there is certain convergence rate. So in general, this is very useful when you are doing something like empirical risk minimization, which is over here in the bottom. Because that has the form of the stochastic optimization, and stochastic gradient descent fits really well. So there are this variety of techniques, which I'm not going to go over, but mini batching, federated averaging, local SGD, and so on, that can be easily implemented in this distributed setup that I just showed. Okay, so for this talk, we are going to introduce we are going to briefly talk about two other concepts. So as we have seen, like for stochastic gradient descent, for convex function, we can have solution, we can have convergence. One other thing can be a non-convex optimization problem. And it can be shown that under smoothness condition and some other conditions, like if you run this SGD type process, then eventually you converge to a zero gradient point. And zero gradient point in the case of non-convex optimization can be a local minima. It can also be a saddle point. But since we are using a first order method, we will have no way to tell them apart, and can most certainly not be a global minima. So, but for non-convex optimization, if we are giving any guarantee of convergence, this is the kind of zero gradient point that we are hoping to reach at. Also, we can go beyond the first order methods, which is this stochastic, beyond the SGD type method. And I will mention that in this talk. This is something like second order method or Newton's method or Newton-Raphson's method, where you take a product of the inverse of the Hessian of the function that you are optimizing with the gradient, and that's your update. That's how you're updating your model. It turns out that here there is certain type of non-linearity, and it's not clear how the local machines are going to compute their local Hessians and how the central machines are going to update them, aggregate them by combining those local Hessians. If there is a way to get a global Hessian, it's not really clear because there is this inverse operation which is inherently nonlinear. However, we will see that we can use some technique to make this parallelizable as well. Right. So this is therefore the setup that we are talking about. And in this setup, we are going to talk about two issues that are not really related to optimization, but really related to this setup. So one of the issue is bandwidth limited communication, because you are sending very high dimensional gradients for the case of stochastic gradient descent to the central server in each iteration, and that's going to cost you some that will have some time taken to send all of these gradients. And the problems are really high dimensional nowadays, so there is some experimental study on this, and this is a picture that I picked up from this paper by Alistair and others. So there they have, like, just let us look at this bar chart and say this is 16 GPUs. That means 16 of those worker nodes. Let's say we are looking at these greens. So in that case, in this bar chart, we are plotting the time. So the bottom darker part, this is slightly darker green, if you can tell that. So that's the time taken per epoch for communication. And the upper lighter part is the time taken to compute the gradient itself. Okay, so as you can see that the communication time is actually outweighing the computational time. So to speed up distributed machine learning, this communication is really a bottleneck, and we somehow need to address that. And this is like a much smaller scale problem, but you can scale it with the modern natural language processing models that can have billions of parameters. So the gradients are actually billion dimensional. So and now I think most recent cases trillion dimensionals even. Okay, so the communication question is the following: that what if you send only few bits of the gradient? So would it still convert? So if there is any fundamental limits of communication versus convergence rate of this type of algorithms, and also to come up with a scheme to do this thing, a communication scheme that will achieve this. The other issue, which is not related to optimization but related to the setup, is the issue of Byzantine workers, which is something well recognized in distributed computing literature from the 80s. It's that you trust all of these machines to follow some protocol and send you some results on their local data, but they may not do that. Maybe they are just adversarial and not doing that, or maybe they just have restriction, or their channels are noisy or something. So there can be garbage sent, or maybe even adversarial things sent back to the central server, which will then completely destroy the optimization process, right? And this, if it is adversarial, so this is adversarial attacks during the training process, and that can be pretty sophisticated as well. It has been seen that even only one Byzantine machine can ruin the stochastic gradient descent, because they can just come up with a negative gradient attack. So they know what are the gradients of all other machines, and they can just send something which is negative of that value. Therefore, when the central server aggregates, it's going to give them 0, and they will think that they have achieved some optimal point, whereas that is clearly not the case. But if there is some way of aggregation by which you can bypass this type of attacks, but then adversaries can collude and they can come up with much more sophisticated attacks, such as saddle point attacks, where they create saddle points close to the local minimas, and the optimization process converges to those saddle points. So for the rest of this talk, these are the two issues that I'm going to discuss. So let's have a more formal model of the Byzantine attacks or Byzantine failures. That's going to be the main topic over here. As you can see, I have this empirical risk minimization problem. So where each fi is actually some loss function, so point-wise loss function, and you are summing them up over capital N data points. However, these data points are distributed among M machines. So each machines in their local data set, they have this local data set. And then the gradient, the update step is that they compute the gradients of their local functions over here, send it back to the central server, and they might wait for they might take few local gradient steps and then send it back to the central server that then updates their parameters using the simple SGD rule. Okay. We are now going to assume that the fraction of Byzantine machines that can be there is alpha. So it means if there are M machines, M alpha of them can send you this this type of adversarial thing or garbages. Okay, so this is the picture, and I have like M machines. A few of them can send you arbitrary things. So what can be done in this scenario? There is a lot of work in the recent years, and this is just a sample of those works. By no means this is comprehensive, and there are a variety of like a few different techniques that people came up with to tackle this Byzantine worker nodes or Byzantine machines. Some of these techniques are following, like they basically follow from the fact that you are doing an aggregation at the central server, which is something like computing a mean. Therefore, you can borrow from the robust statistic literature and see how do you do robust mean estimation. Right. So, and there are a few techniques. One is, for example, coordinate-wise median. So instead of aggregating, summing up all the values of the local gradient, you can actually take the coordinate-wise medians of those vectors. And of course, the linearity properties are all lost. So it will be some work to show that SGD actually converges. You can also do something like trimmed min, where you take a subset of these vectors and then compute the mean over there. There is something called gradient clipping, which is very much related to the gradient clipping is going to be very relevant to us. So in gradient clipping, that has been used in the literature of differential privacy and also to tackle exploding gradients in training neural networks. So what do they do is they like if the value of the gradient or the norm of the gradient is beyond certain threshold, they don't consider those gradients for the time at the aggregation time. There is also recent work where people consider geometric median instead of coordinate-wise median, and there can be certain benefits of this. Now, these are more or less all the methods that are out there and combinations thereof, but none of this talks about communication efficiency at the same time. So the only work that I'm aware of that talks about both communication efficiency and Byzantine resilience with the same process is in this paper Sign SGD from 2018. However, there are certain drawbacks for it. So Sign SGD here, you just send the coordinate-wise signs of the gradients. So instead of sending all this high-dimensional vector, you are sending high-dimensional binary vector. So that gives you some advantage in terms of communication. But these methods are not known to converge in general. You have to assume a bunch of different things to show that such type of SGDs are going to converge. And they can also tackle only limited type of adversary, and there are limitations of this method. So, but however, this is probably a very relevant prior work from what I'm going to describe. So now let me give you a method which is very much similar to gradient clipping, but not quite. And that's what our method is. It goes very well with certain communication efficient, certain compression methods as well. So here is the method. So you have this M machines, and you know that at most alpha m of those machines can send you garbage or like adversarial values. So what you are going to do is to sort, once the central server receives the gradients from each of the machines, it's going to sort according to the norm of the vectors, right? So now this is a sorted list of the gradients. And after that, you do a norm-based trimming or norm-based filtering, where you just keep 1 minus beta fraction. Well, you basically discard the beta m fraction. I think I lost my slide again.
Your slides disappeared again.
It's back again, right? Yeah.
Yeah.
Might happen again. I realize the problem. Not going to change much now. Okay, so I have beta, which is a number between 0 to 1 and strictly greater than alpha. I'm going to discard beta m of those gradients, and whatever is left, 1 minus beta times m. I'm just going to aggregate the gradients over here. Now, it can, since I have just sorted by this, can good machines get trimmed? Yes, that can happen. And some bad machines, the bad values can be aggregated over here. So whatever we have here, we are calling that a robust update. So now the intuition behind this method is actually pretty straightforward. So when a corrupted gradient is being sent, if the norm of that corrupted gradient is not too high, then it's not going to affect our aggregation method anyway. And if it is too high, just by discarding the top, like the highest beta fraction of the gradients, I'm going to get rid of it. Okay, so all of the good machines, the good gradients all of the bad gradients that I have in this top half over here, their norm cannot be, exorbitantly high. So therefore, they will not be able to destroy whatever is the good gradients the aggregation of good gradients giving us. And you can see that all this negative gradient types attack that can be thwarted by this way. Now, what can we say about the performance of this? Well, again, we have to show theoretical result. We have to make certain assumptions. So what are our assumptions? Our assumption is that the loss function is smooth and local gradients are sub-exponential. So that means we're assuming some randomness property of local gradients, and it can be shown that this is not, local gradients being sub-exponential is not a very big ask if you assume that eventually this is this is a gradient of a loss function, right? And the loss function is computed over data points. If those data points are generated IID by from some distribution, then this usually follows. So if this is and this has been used in some prior works as well, so it's not really that we are showing this. But if we make this type of
Arya, sorry to interrupt, but if you could wrap up in the next minute or so, that would come next.
Right. So if you can, so what are we going to get with this? So if alpha is less than beta, turns out that if 4 alpha plus 2 beta is less than 1, then what ends up happening is that this process that I just described is going to take you to this 0 gradient point. Okay. It turns out whatever is this rate of convergence, that is also optimal by some lower bound in a previous paper. Now, in the next 1 minute, as I said, I'm going to wrap up by saying that we can actually combine it with some communication efficient scheme. So there is this generic thing called delta approximate compressors, where you take a gradient, you compress it, and it turns out that, so if it follows this type of property, which is very much like rate distortion, if you are an information theorist, then this is going to be called a delta approximate compressor. So delta equals to 1 means there has been no compression, and delta equals to 0 means you have compressed it to 0 bit. So you can actually combine this method with this type of compressors, and what you are going to get is exactly similar type of convergence result, but instead of 4 alpha plus 2 beta less than equal to less than 1, you are now going to get 4 alpha plus 2 beta less than delta. Okay, so I'm just going to skip over this and just want to mention that you can actually have distributed Newton's method, and there also both of these methods of communication efficiency and Byzantine robustness going to work. Not only so we can do norm-based filtering for certain product of local Hessian inverse and gradient. It turns out that you can still show convergence at a faster rate than the stochastic gradient method, because of course this is second order method. So all of this fits in, and they really work well in real data sets as well. So furthermore, there are other sophisticated techniques that actually to deal with saddle points, and this norm-based filtering and the communication efficiency works to make those methods distributed as well. So I'm just going to summarize. This was based on these three things. So one paper has appeared in Journal of Selected Areas of Information Theory recently. There is the second order method and the saddle point. So that has appeared like in the last couple of years, and this one is the method to tackle saddle points is still under submission. Okay, that's it. I know that Mary likes stick figures, so so I thank you all, and if there is any question, I can take them.
Thanks so much. Maybe in the interest of time, we can take questions offline.
Sorry for going over time.
No worries.
But I hope that the main message was.
Absolutely,
Okay,
yeah. Thanks for
lot.
the time for this talk.